My name is Wendell Bates, a PhD candidate in electrical engineering under the advisement of Dr. Karamidini. And today's talk will be about events-based fault diagnosis for partially known discrete event systems. So there's a host of different types of systems in the world today, especially here at North Carolina A&T. We have a bunch of autonomous systems where we have UAVs in the lab, we have humanoid robots, and we also have UGVs or autonomous car projects as well. However, as many of you know, all of these different systems are prone to faults. And so a fault can be defined as anything from a deviation of a system from a specified acceptable operation or an abnormal condition that can cause an element of the system to fail. And so they're usually separated into two different categories, where hardware and software, where hardware fault could be a loose or broken wire, and a software fault could be a coding bug. And so we need fault diagnosis because, in spite of the mass amount of intelligent minds that we throw at system analysis to improve their reliability, faults are still unpredictable, and anything that can go wrong will go wrong. And so in literature, there are ways to attack fault diagnosis using redundancy, but it's not always feasible to place sensors upon sensors. And so these are a couple of the developments that we've come up with here at Access Lab and Tech Lab concerning fault diagnosis. Event-based fault diagnosis for unknown plant, or semi-asynchronous fault diagnosis of discrete event systems, just to name a few. And so the case study that I'll be applying the research to, that I'll be talking about today, concerns the Boeing 737 MAX. And so the Boeing 737 MAX, many of you might be aware of the history of this aircraft. In October 2018, there were unfortunately 189 casualties. And then not even 6 months later, another Boeing 737 MAX tragically crashed, resulting in 157 casualties, resulting in 346 total casualties. And so the outline of the rest of the talk today will be about modeling the Boeing 737 takeoff procedure, fault diagnosis of the Boeing partially known system that we derived from the model, simulation, and then properties of the algorithm, conclusion, and any questions. And so we begin with modeling the Boeing 737 MAX takeoff procedure. A bit of history about the Boeing 737. It was first introduced to the public in 1968. It was developed to supplement the Boeing 727 on shorter routes. It's the most ordered plane in commercial history in 1987, and the latest generation, one of which we'll be discussing today, is the 737 MAX 7 through 10, which entered service in 2017. A point I'd like to highlight is that the 737 MAX airplanes are powered by a new and improved CFM LEAP high bypass turbofan engines. And these are just a couple more specs regarding the Boeing 737 MAX. And so first I want to get into a bit of the airplane dynamics. So to describe how an aircraft moves in space, there are three imaginary lines that pass through the center of gravity of an aircraft that, in regards to the roll, pitch, and yaw, what we'll be focusing on for this talk will be the pitch, which is the motion of the aircraft along its lateral axis, and the pitch is controlled on the airplane by elevators. And so a bit of history behind the beginning of the story is, so manufacturing companies continuously are facing constant pressure to keep up and compete with each other when it comes to building cheaper airplanes, mainly focusing on improving the fuel efficiency. And so in 2010, Airbus, which is Boeing's main competitor, pretty much shocked the aviation community, announcing that they had built or had developed and were building a more fuel-efficient aircraft called the A320neo. And their claim was that this new aircraft would burn 16% less fuel. And they were planning on having the neo available for full commercial operation by 2016. And so in an aggressive attempt to remain competitive, because so many people were interested in the new A320neo, in 2014, the CEO of Boeing announced a new larger engine design. And the larger engine design, instead of creating a whole new airplane, the larger engine design would be based around the base model of the previous 737 aircraft. However, when it was fit on the old base model, the new engine didn't properly clear the ground. And so it had to be moved up and forward on the wing structure. So as you can see here, it's highlighted as to what the engine looked like on its placement on the wings. So during the initial flight test, the test pilots were complaining about the high pitch rate that occurred during takeoff. And so to add insult to injury, studies show that 20% of the aviation fatalities occurred during taxiing, takeoff, and the initial climb. So this was something that they couldn't move forward with producing the airplane without fixing. And so the reason this is so dangerous is because a high pitch rate causes the angle of attack to be too high. And so the angle of attack is the angle between the oncoming air and a reference line or where the airplane is going. And too high of an angle of attack causes the airflow across the upper surface of the wing to become detached, which results in stall. In order to combat this high pitch occurrence, Boeing developed the Maneuvering Characteristics Augmentation System, which is MCAS for short. And so the responsibility of the sorry, I thought I heard you. So the responsibility of the MCAS was to automatically push the nose of the plane down in order to aid the pilot in case of irregularly high angle of attack was detected. And so typically MCAS was supposed to work in the background and the pilot would really never know it's there. And so once the crashes occurred, Boeing 737 MAX was grounded indefinitely. Numerous investigations were put in place, and it was found that among some of the failures that caused the planes to crash was that the MCAS depended on a single angle of attack sensor, which resulted in single point failure. So there was no way for there to be any type of correction. And one of the angle of attack sensors was found to differ by 20 degrees. Also, when MCAS was created, it was quote unquote hidden. And so the software and its functions weren't disclosed to the pilots in order to decrease the time it would take for them to launch the airplane and also decrease the cost for increased pilot training requirements. And on top of that, the MCAS information was removed from the flight crew operations manual. Another thing to note is that the significant increase for the movement of the plane's horizontal stabilizer, the MCAS, when the MCAS was active, if you were going to override it, it required more manual power from the pilots. In the case of the MCAS reading the angle of attack sensor differing by 20 degrees, the pilot would essentially lose complete control of the airplane. And so there are different modes for takeoff that I want to go over of an aircraft. You have the runway acceleration, then you go into the initial climb, and then you go into the flaps up, where the flaps are retracted and the landing gear is retracted. And then you have your en route climb until you reach your cruising altitude where autopilot can be turned on. And so we choose to model, in our research, we choose to model these different systems as discrete event systems. And so the reason being is because discrete event systems are able to provide a model for high-level behavior, which is captured by a sequence of events, and also represent logical system behavior in a more useful way. Also, any faults that occur in the system can be considered as abrupt changes or events in the system. And so what is an event? So an event can be any specific action taken within the system, like a button press, as you can see Baby Yoda pressing the button when he's not supposed to. Any observed spontaneous behavior, such as an assembly line shutting down for no apparent reason, all the way to a system exceeding the maximum and minimum threshold of a continuous signal. So there are different types of discrete event system models. We have Petri nets, process algebra, and automata. We use automata in our modeling because it provides an intuitive and visual representation of the system that makes composition operations and analysis more manageable. So the automaton structure is mathematically described as follows. It's based off a tuple where X is the state space, which is the circles with numbers inside of them. The event set sigma, which is composed of observable events like sensor data transfer, or unobservable events such as sensor damage. Defaults are considered unobservable events, and then you have the transition relation as well as X naught, which is the initial state. And so you also have strings, which is a sequence of one or more events that's allowed by the system's behavior. And the language is the set of all system strings which originate from the system's initial state, X naught. A mathematical tool we use to represent the visibility of the behavior of the system is the natural projection. Natural projection can be extended from events and strings to the language. And also the inverse of the natural projection allows us to reveal any unobservable events that might have occurred within the system's language. And so we'll begin with the model construction. So the assumption when we're getting into the model construction of the takeoff procedures that we're starting at the beginning of the runway. All standard pre-flight checks have been approved. There are no errors that have occurred before the start, and the air traffic controller has approved the takeoff clearance. And so when we begin, runway takeoff has can be best described with 3 different stages in velocity. So V1 is the speed where takeoff should no longer be aborted. If the engine fails before the V1 velocity is reached, the pilot has to abort the takeoff, and the aircraft systems will immediately cancel any thrust and apply the brakes. So in circle 1, you see the runway takeoff acceleration. While we're in this mode, if the engine fails, like I said, we then move to state 2, and the brakes are then applied, and we're in state 3. If all is going well, we continue on to state 4, which is the initial takeoff climb. And so then we get into the en route climb. So during the en route climb, the pilot has to manually maintain the proper pitch and angle of attack for a successful climb. And then upon once the climb is stabilized, the landing gear is retracted again, and the wing flaps are retracted to achieve optimum lift. So when you do this, the pilot has to be aware and anticipate any sudden changes that the angle of attack might change within the angle of attack upon retracting the gear and the flaps in order to avoid stall. And then continuous pitch adjustments have to be made by the pilot, whether bringing the nose up or down through pulling the control stick or pushing the control stick until you reach a cruising altitude, and then autopilot mode can be set. And so then this is our model construction of a model takeoff procedure under normal conditions. And then this is the model once the if the MCAS was introduced. And so remember, the MCAS is set to active in the background after the airplane's flaps have been retracted. Upon activation, the yoke pull is deactivated in order to avoid any manual interference by the pilot while the MCAS is correcting the pitch. And you can see that in red with the dotted or dashed gray lines, due to faulty software implementation and incorrect angle of attack sensor data, the nose of the plane was immediately pushed down during takeoff. And so now that we have our model, we can go into fault diagnosis for the Boeing 737 MAX. And so in the model that we've created, you see there are different types of faults within our system. Fault events are unobservable, otherwise their diagnosis is trivial. And so we have the known portion of the system, which is, we say that this is known because this is what pilots are trained on. This is what they're aware of. Anything that could go wrong during this time, they're knowledgeable about. And then we have the unknown portion, which was introduced with the intention of making the system of the Boeing 737 less complex. However, if you recall, this part of the system is unknown to the pilot. And so there are two strategies when attacking fault diagnosis of a partially known system. Strategy one could be ignoring the available information and then treating the system as a completely unknown system. And so we would start from the beginning and then continue to learn the system throughout. Strategy two is taking advantage of we could take advantage of the already available information and then begin to learn the unknown portion. And so when it comes to learning, there are two different types of learning. There's passive learning methods where a set of training data is supplied to the algorithm for model construction. However, the drawback is you cannot adapt to new situations that will require new information, and it's also susceptible to missing information. In order to combat this, there's active learning techniques which continuously engage in the system and have the ability to inquire about any of the missing information. So it's more of a conversation between the algorithm and the system. And so this is the contribution of the work where we're considering a deterministic discrete event system where part of the system is known, and then based upon the observable parts of this string generated by the entire system, how do we determine a fault occurrence in the system and diagnose any faults that have occurred? And so the diagnoser would look like something that you see in the center, the middle bottom, which we'll get into in just a second. And so the functionality of the diagnoser is diagnostics, to provide diagnostics of the system under analysis. Using the observable behavior of the system, the diagnoser is able to reveal information about the system's current state, whether we're faulty or normal. And then upon the occurrence of an observable event in the system under analysis, the diagnoser then will update the information on the system's condition. And so now this step is taking into account the known part of the system. And so those steps are to build the diagnoser for the known part. And these are some references to the literature that have been done on when you know the system, how to build a diagnoser. And then we get into capturing the information from the known part into tabular form. And so first we build the diagnoser for the known part using this algorithm. And then, like I said, we capture the known information into tabular form. And so the information is captured into data structures that we call observation tables, which can be measured or represented as a tuple as well, S prime, E prime, and T prime. So the rows and columns contain different strings. Rows in S prime represent distinct states in the automata, and rows in S prime sigma minus S represent states that might be reachable by events from a row or state in S prime. And both of these are non-empty prefix closed set of finite strings. And then the columns in E prime represent experiments where you're testing for any new states that might exist. And E prime is composed of non-empty suffix closed set of finite strings. And so first we use L hat, which is the minimum length of the events it takes to cover all states in the diagnoser. And so for this particular diagnoser that's been built, the length is 4, and then that we then begin to fill the table. And so with the observation table, 2 important characteristics I want to note are consistency and closeness. So consistency exists if there are two rows in S prime that are the same, but no concatenation of any event to the end of the string results in a new state, then the table is consistent. If it does, then you add that event to the set E prime, and then continue to construct your table and fill it out accordingly. And so consistency ensures that the automaton we're representing is deterministic. And then for closeness, a table is closed if and only if there's no row in sigma, S prime sigma minus S prime that is not in S prime. If there is, then that row needs to be moved to S prime, and then the table should be extended accordingly. And so closeness ensures that all possible transitions to all existing states exist. And so once we capture the information, we then begin to fill the table. So because the table is so huge, this one in S prime alone creates 780 rows. I will go over reduction in a second. And so now the next part, once we have the known information, we've built our table, we've constructed the table based on the known information, we then go to learning the unknown part of building the diagnoser. And so the rest of the diagnoser structure is as such also represented as a tuple where Q represents the diagnoser states, QDK is the known diagnoser states, QDU is the unknown diagnoser states. You have your event set, the diagnoser's transition rules, the output function, and Q0, which represents the initial state. And so in order to begin this, when we get into the active learning part of learning the unknown information, we make queries to an oracle. And 2 queries are membership queries does a particular string exist in the projection of the language of the system? And is the string faulty? And then we have equivalence queries, which says, does the language of our diagnoser equal the projected language of the system under analysis? If it doesn't, then the oracle provides a counterexample that exists within the symmetrical difference between the languages. And so for the unknown part of the information, we the mapping function is a little different. So when you know the information and have access to a system, you're able to tell you're able to provide that state information. In this case, we don't have that state information. We just have the whether or not the event occurred. And so all we can do is label whether or not those events are faulty. And so so instead of a number, we represent the quote unquote state information with a star, which signifies that the state is unknown. And if the string is normal, then that no fault has occurred within the inverse projection of the string. And so if the inverse projection of the string provides faulty labels or faults in all strings, then the label will then be will be represented by an fi, whichever fault has occurred. And then if we're not sure if the inverse projection provides a string that's non-faulty and a string that's faulty, then we call that ambiguous, and that's represented by an A. And so this is the algorithm that we use in the algorithm's flowchart. So the table we constructed for the known part V prime is set to V1. We then construct the zero sets, which I will go over in just a second, and then revise V1. And then we check for consistency. If the system is not, if we find that it's not the table is not consistent, we make the table consistent. We check for closeness. If it's not closed, we check or we make the table closed. And then if it is consistent and closed, we then construct an automata. We ask the oracle concerning equivalence query of the language. And then if the oracle says no, the languages are not equivalent, it will provide a counterexample, and you will then check for consistency and closeness again until you construct a language equivalent automata, and that will be your complete diagnoser. And so what I was talking about earlier, because the tables were so big, a way to reduce it simply for visualization purposes is any row, all the rows that are zero, you can somewhat ignore after we get into the zero row sets. So the zero element sets consist of Z, ZM, and Z counterexample. So we don't need to look, because we already have the known information, we don't need to look at anything we already have. We only need to focus on rows that are zero. And so Z is the set of all zero elements within the table. And then ZM is constructed. We ask the oracle, do these exist in the unknown portion? And so ZM are the strings that exist in the unknown portion, and then Z counterexample is the shortest string in ZM, and we use that to continue learning information about the unknowns. And so here you can see in V1 from the system under assessment, AAB was found to exist, as well as AAABB and AAABD. And then that information was changed. So in B2, you can see row AAAB is now showing a star as well as the label, which is ambiguous 1. And then AAABB is added as a counterexample, and then the table is continuously extended. And so throughout the algorithm, we continue to check for consistency and closeness until we reach a final consistent and closed observation table that allows us to create our diagnoser, our final diagnoser. And then from the table, we use these equations to then build a complete diagnoser ready to assess the system under test. And so a simulation of how this works is, so on initial takeoff, we're on the runway, we're entering takeoff, acceleration, no engine failures have occurred, so the pilot begins to pull back on the control stick. We begin our initial takeoff climb, so we're still normal, as you can see in the diagnoser on the bottom right. We then get into flaps up, and then we start our en route climb. However, in the case that the MCAS was working in the background, the plane would immediately start to pitch down. And so the pilot's initial reaction would be to pull back on the control stick in order to make the plane pitch up. The plane would not respond and would continue pitching down. And as you can see, the diagnoser shows that upon that event or occurrence, that the system would be faulty. And so we believe that this is a tool that could be used in conjunction with other safety requirements in order to potentially save lives because the pilots were unable to know what was going on. And so a very important property of the diagnoser is diagnosability. In the top right is the equation for FI diagnosability if you have access to the system, but when you don't, we have come up with a sufficient condition that says if you have no cycle of ambiguous states within your diagnoser, then you can say that that system is diagnosable. So for the system we built for the Boeing 737 MAX diagnoser, it is both F1 diagnosable and F2 diagnosable. An example of a diagnoser that would be undiagnosable for a fault is the example I'm showing here. If you can see the red dashed lines, that there's a cycle of ambiguous 2 states, so the system is not diagnosable for fault 2. But since there are no cycles of ambiguous 1 states, the system is F1 diagnosable. And so the properties of the developed algorithm is we've developed a novel technique to construct a diagnoser for a partially known system. We're able to capture the information from the diagnoser corresponding to the known part in tabular form. We utilize active learning to discover the unknown part. The algorithms terminate in a finite number of iterations. We've derived the condition to verify diagnosability and obtain an upper bound for diagnosing a fault. And so in conclusion, we've developed a model for the takeoff procedure for an aircraft, specifically speaking, the Boeing 737 MAX. We developed an algorithm for the construction of a diagnoser when it's applied to a partially known system, derived the condition to verify diagnosability, and we've, as you've seen, we've applied the technique successfully to a constructed diagnoser for a Boeing 737 MAX case study. And these are publications that I have finished or am also currently working on. And a special thank you and acknowledgement again to Dr. Karen Medini, Dr. Amai Farr, my friends and colleagues at Access Tech Labs, the Air Force Research Laboratory, and Department of Defense,